Going to be going over organic chemistry, not all of it, but some parts of it. Okay, so the first definition I want us to look at is the definition for a homologous series. So let's just do this. So a homologous series is defined as a series of compounds that have the same general formula and the same functional group. Each member of the series differs from the previous member by a CH2 group. So we're going to look at examples of different homologous series, and we will show everything that they have mentioned here. We will show how they have the same formula. We will show how they have the same functional group, and we will show how each one of them, one from the other, they only differ with the CH2 group. Then we come to saturated and unsaturated molecules. So for our organic chemistry, we are going to have carbon as the backbone of all the compounds. Now, carbon is very special because it can actually have a single bond between the carbons. It can have a double bond between the carbons, and it can have a triple bond between the carbons. Now, when it has only single bonds between the carbons with nothing else but looking at the carbons, we regard it as saturated. So saturated compounds are compounds in which there are no multiple bonds between the carbon atoms in their with regards to also their hydrogen chains. Right. So there will be definite chains over here. Then we have saturated. So saturated, we will definitely have multiple bonds. So it could either be a double bond or it could be a triple bond between the carbon atoms in their hydrocarbon chain. So very important here. The word is hydrocarbon. A hydrocarbon is a compound that only has carbon and hydrogen. So in terms of hydrocarbons, we have 3 types of hydrocarbons, and we will look at those. So when we are talking about a saturated or unsaturated compound, we're going to be looking at specifically hydrocarbons and nothing else. Then we have what we call a functional group, which is a bond, an atom, or a group of atoms that determine the physical and the chemical properties of a group of organic compounds. Okay, so now we're going to be looking at the different homologous series we have. Their formulas, their functional group, and we'll be looking at suffix, prefix, just for the naming part. So these are the different homologous series that you will be looking at. For IB, you won't have ketones and aldehyde, but if you're doing CAPS, you will definitely have everything that is on this list. Now, let's look at our hydrocarbons. We have 3 different types of hydrocarbons. We have your alkanes, your alkenes, and your alkynes. The difference between all of these is an amount of bonding that we have between the carbons. For our alkanes, we have a single. For our alkenes, we have a double. And for our alkynes, we have a triple bond. Again, for IB, the alkynes, you won't find much of them, but the alkanes and the alkenes, you'll definitely find a lot of them. So we have the general formula for our alkane here. which says Cn is equals to, or CnH2n plus 2. This tells us that if we have 2 carbons, then we will have 2 times 2 plus 2 number of hydrogens. That's what this is explaining. We can see it's different from alkenes because it has now 2n only, and then for alkynes, we will have to then subtract 1. So when we are naming our alkanes, we're going to put the suffix or at the end an in and a. If we are naming our alkenes, we'll put an in, and if we're naming our alkynes, we'll put an ein at the end. So let us say that we have a carbon that has, or hydrocarbon that has 3 carbons. For the alkanes, we will have what we call a propane. For the alkenes, it will be propene, and for the alkynes, it will be a propyne. Over here, they try to show us the structural formulas of these hydrocarbons. You can see here we have 3 carbons, and we only have single bonds between the carbons, and everything else is just an attachment to hydrogen. This here is an example of what a condensed structure is going to look like. So now when we write a condensed structure, let's say for our propane, which has 3 carbons, and everything else is a hydrogen. And according to this, there should be 6 hydrogens there. So when we write our condensed structure, we will first take a look at our initial group, which has 1 carbon, 3 hydrogens. Then the group next to it would have 1 carbon, 2 hydrogens, and the one at the end will have 3 carbons. Now, previously, when we were defining what a homologous series is, we said that they must have the same functional group. So the functional group in the alkanes would just be the single bond. The functional group in the alkenes would be a double bond. And the functional group in the alkynes would then be a triple bond. So we said that the only difference between the members is that they will differ by CH2 group. What do we mean by that? Let us say that we had now an alkene where the number of carbons was now 4. According to the formula, the number of hydrogens would be 2 times 4 plus 2, which would give us 10. So if we draw our structural formula for we're going to call it a butane, but we'll come into naming and you'll see why we call it a butane. So the structural formula for butane would be 1, 2, 3, 4, and we will just have hydrogens everywhere, hydrogens everywhere. This was supposed to be for 3, sorry. So then the number there, it's not 6, it is 8. Okay, so if we wanted to show the condensed structure, we would have CH3, sorry, CH2, CH2, and CH3. We can see that the difference between the previous alkane, which had 1 CH2, and this, which has 2 CH2, the difference between them would just be a CH2. And this is also going to be true when we have double bonds or triple bonds. Then let's look at other types of homologous series. We have your haloalkanes. Your haloalkanes look like your alkanes, right? These ones. The only difference is one of the hydrogens is going to be substituted in by a halogen. When we talk about halogens, we talk about fluorine, chlorine, bromine, and bromidite. So this is the second element from your noble gases, right? Your noble gases being neon, cyan, and krypton all there, that side, helium. So we have our halogens. So instead of having a regular propane, one of the hydrogens is going to be replaced by a halogen. In this case, I chose to replace it by a chlorine. Okay, so because it's similar to the alkanes, its suffix is also the same as the alkane. The only difference is when we name it, we will see that we have a prefix that tells us where to find that specific halogen that we have substituted in. Okay. And the formula here almost looks like the alkane, but it's not, because it says SaH2N. Instead of saying +2, it says +1, and then we then have to add one halogen. We have alcohols. What is special about alcohols is that they are going to remove that hydrogen in the alkanes, and they're going to substitute in a hydroxide. Right, and that's what we call the functional group of alcohol. So it's going to be the same as the halogens. It's just that the difference here, we would say add a hydroxide, not a halogen. So it's almost like substituting into our alkane again, but it has a different suffix when naming it. We say all when we're naming it. And again, we need to indicate where that hydroxide is by showing the numbers, but we will get to the naming. The next one we have is aldehydes. Now, aldehydes have removed a hydrogen so that they can substitute in an oxygen. Now, because an oxygen requires a double bond, so we would not add one, we would add nothing, because we need to take those two hydrogens and then give them to a double bond with oxygen. Now, the thing about aldehydes is that it's only an aldehyde if the oxygen is attached to the last carbon. It's only an aldehyde if the oxygen is attached to the last carbon. And in terms of naming, we will write an Al as our suffix. As you can see here, if we had an aldehyde with 3 carbons, we will just call that proper now. Then we get to the ketones. The ketones, if you look at that, they have the same general formula as your aldehyde. The difference between your ketones and your aldehyde is that the double bond needs to exist anywhere but the end. We can't put it in the end, because if we put it in the end, it's an aldehyde, so it must be in between. So if the double bond with oxygen exists in the middle, this is not a good drawing of it. This is a good drawing of what we want. It must exist in the middle, because when we put it outside, it is an aldehyde. It is no longer a ketone. So the ketones, we're going to write the word one, but we pronounce it as ones for the ketones. Then we're going to have a special one called carboxylic acid. In the carboxylic acid, we will have 2 oxygens there. We will have a double bond with one of the oxygens, and one of the oxygens is going to be attached to a hydroxide. You will notice that the carboxylic acid and the esters also have the same general formula. The difference between the carboxylic acid and the esters is that after the double bond, yes, the oxygen is connected to the carbon, but it won't be connected to a hydrogen, it will be connected to another carbon. So with the carboxylic acid, that oxygen is connected to a hydrogen, and it's going to be at the end of our molecule. This is our functional group, whereas for the esters, it's going to have a single bond to another carbon, and the chain can continue. So for our carboxylic acid, we're going to write an anoic acid to the name, to the end of our name. And then for the ester, an ester has a two-part. So an ester is going to have a chain, and it's also going to have part of the first name, which is an anoate and an ethyl, but we'll get to the naming of our homologous series. So it is very important for you to be able to draw your compounds as a structural formula and also a condensed formula. You need to know the difference. Now, when it comes to our organic molecules, they can exist in what we call isomers. Isomers are said to be compounds that have the same general formula or the same formula, but they will then have different structural formulas, and they will also have different names. Now, the type of isomers we have different types of isomers that can exist. The first type of isomer that exists is due to its chain, the chain structure, how it actually looks like. It might be confusing if you haven't yet done naming, but what I want you to focus on is how different the structures are from each other. So here we have two chains. In this initial chain, we have 1, 2, 3, 4 carbons, and according to our equation, we should have 4 times 2 plus 2, which is 10 hydrogens. So we have 10 hydrogens, and this is called a butane. You will note that the chain is a straight line chain, right? Whereas here we have a straight line chain, but it has branching. We call this branching. Right? The straight line chain is made up of 3 carbons, whereas there is a carbon that is then going to be attached to the overall structure, and we call that branching. Now, the way we will name it, we would say it's a 1-methylpropane. This is a bad name. It should have been a 2-methylpropane, implying that we substituted, instead of having hydrogen there, we substituted a whole methyl compound. Now, if you look at the molecular formula, you'll see that both of them possess 4 carbons and 10 hydrogens. So the molecular formula is the same, but the structural is not. We call these chain isomers. So these are the first chain isomers that we have. They have the same molecular formula, but they have structural differences. Okay. Then the next type of isomer that we are going to have is called a positional isomer. It might look like they are the same, but they're not, because the position of the substituent is not placed on the same position. So let's have a look at them. Here we have 2 alcohols. Now, when it comes to naming, it is very important for us to say where the alcohol, on the chain where the alcohol is found. Here we have a structural chain that has 4 carbons, 1, 2, 3, 4. Here we have 1, 2, 3, 4, and we can tell the straight line, both of the straight lines have 4 chains. That's the bute part. The bute stands for 4. The difference between this chain and that chain is where we substituted in our alcohol. So this falls under the homologous family of alcohols. And for the first one, we substituted in carbon number 1. So we say we're going to call it tan, 1 to show the position, all. We did say that the suffix for alcohols is all. Then for the next one over here, we have but, tan, 2, all. So the 2 then goes on, it implies that the 2 is on your second carbon, and that is why it says it's a positional isomer, because the position in which you find the alcohol is different. This alcohol does not have the same structure as that alcohol, although if we look at their molecular formula, we would see that they both have 4 carbons, 10 hydrogens, and 1 oxygen. They might have the same molecular formula, but they clearly have structural formula. Different structural formulas, I mean to say. The last type of isomer we're going to have is the functional isomer. Right. So the molecular formula is going to be the same, but the functions will not be the same. Now, before we look at this picture, I want us to go back to this list of our homologous series. If we look at aldehydes and ketones, we will see that the general formula for aldehyde and ketones are the same. They are both the same. So aldehyde and ketones can be functional isomers to each other, because even though both of them have a double bond of oxygen, where the oxygen is situated is not the same. And carboxylic acids and esters make good functional isomers, because again, if you look at the formula, you would see that the general formula for the homologous series is the same, but the way the compound is structured is not going to be the same. So whenever we talk about functional isomers, you always have to think of the two. It's either going to be an aldehyde with a ketone, or it's going to be a carboxylic acid with an ester. If you are doing IB, just know it's always going to be the carboxylic acid with the esters, because IB does not do aldehydes and ketones. So let us look at this example that they have provided us with. Okay. Here we can see that they chose to use the aldehyde and the ketone. This should be ketone, that here should be an aldehyde. Right. How do we know it's an aldehyde? The double bond is on the last carbon. If the double bond is anywhere but on the last carbon, it is the ketone. So even if it was here, this will still be an aldehyde. If it was on the last one, aldehyde. Only when the double bond with oxygen is in the middle is it seen as a ketone. We can see if you look at the molecular formula looks the same. They both contain 4 carbons. They both contain 8 hydrogens. They both contain a single oxygen, but they are of different functions. One is a ketone, and the other one, they should have written here, aldehyde. So this is called a butanol, and that is called a butanol. So they are different. They will have different properties, and that is what isomers are. So now we're going into naming compounds. So when we go into naming our compounds are going to be a 3-part naming. So the first part we have is our substituents. Right? This is the chains that we are going to add. And not only do we write the substituents, we also need to tell them on what position carbon the substituents are. When we list these side chains, they're going to be in alphabetical order. Then the next thing is to look at the root. The root is focused on the main chain, right? The main chain does not have to be straight, but you have to be able to draw a line from the point where it starts until it ends without having to lift your pen. Then we have your suffix, which is dependent on the homologous series. We saw the different names, the different homologous series having different suffixes. So let us look at, before we even do that, it is very good. It's going to be important for you to know in terms of the long chain, what you should name them. So we have this table, I'm sure that they would also provide in your school, where if you have, in your long chain, if you have 1 carbon, it's meth, 2 S, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and if they ever go to all the way to 10 is dec. So let's take a look at how we're going to name these. Let's have an example. So this is our example. It is a 3-part, right? We have, I would advise for you to start with the root. The root is very important because you need to identify first your longest chain. Now, for my longest chain, your longest chain will always include the functional group. If it does not include the functional group, something is wrong. So in this case, I could go straight or I could go this way. Either way, I have 3 compounds. So it doesn't matter. In some other situation, it would matter, right? If this one had an extra, let's say it was H2 and then H3, if this one had an extra CH2, then the longest chain would go this way and not that way. But because whether I go straight or I go left, it's one and the same, it really doesn't matter what I choose. So for convenience sake, I'm going to choose going this way. Now I need to number my carbons. The first carbon must be the one that is closest to either my substituent or my functional group. I always prefer starting with my functional group, but I need to make it so that the numbers make sense. Hopefully we get an example like that where I can show you which one you need to then prioritize. So in this case, I'll start numbering my carbons, and I'm going to start numbering them at the carbon where close to the carbon with the functional group. So that will be carbon 1, carbon 2, carbon 3. So clearly, with regards to my root name, because there's 3 carbons, it is a prop. Right. And with regards to my suffix, because of that double bond, it is an in. And because the double bond is at carbon number 1, we take this carbon, it should be a 1 in. Normally with ins, we also don't like to show. With one where we have it at 1, we don't normally show the numbers, but just to get us on the right track in terms of naming, let's go ahead and name that as 1E. Then we will see that this is now going to act as a substituent. So now we're looking at the prefix, which is the substituent. We can see that it is attached to carbon 2. And because it has 1 carbon, we're going to be using mat. Now, for our substituent, we always write li at the end. Methyl, propyl, butyl, pentyl. Those are our substituents. Now, let's put the name together. We start with our prefix. We say 2-methyl, one in, we forgot the position. So that's our suffix, our root, and our suffix, and our, prefix, root, and our suffix. So now we have a full name. Let's go ahead and look at another example. Okay. So this is a hydrogen, is just not visible. So now we're going to look for, the first thing is to deal with the root, look for the longest chain. We can go this way, we can go that way, we can go this way. Now, if we go the first way, we have 1, 2, 3, 4, 5 carbons. If we go this way, we have 1, 2, 3 carbons. If we go that way, we have 1, 2, 3, 4, 5 carbons. So we can see that going this way and going that way makes no difference in terms of the length of the chain. So which one would we go? The one that where the substituents are much closer to each other would make more sense, but it looks like they are both at the same. So it really doesn't matter whether we go this way or that way. We still have just 2 carbons going, 2 carbons going. So let's just preferably go in that direction. So we have 1, 2, 3, 4, 5, and that will give us a root name with pent. Okay. Then that implies that this is a substituent and that is a substituent. So when we're looking at the substituent, the first substituent, okay, in terms of numbering, we are going to number it so that our substituents have low numbers attached to them. So if we were to number it this way, 1, 2, 3, 4, 5, the first substituent we see in the list is at number 3. But if we number it this way, 1, 2, 3, 4, we will see that the first substituent is at number 2. So we would prefer having it as 1, 2, 3, 4, 5 instead of going the other way. So we can see at carbon number 2, we have a substituent and it has 1 carbon. So that's a methyl. At carbon number 3, we have substituent and it has 2 carbons. So that's an ethyl. And because all of them, all the carbons are single bonded, so then the end name or the suffix will be an in. So let's put this together. When we write our substituents, they need to be in alphabetical order. E comes before M. So we're going to have 3 ethyl, 2 methyl, pentate as the name of our structure. Let's take a look at another one. So here we have a chain. We can see the longest chain is just going straight forward, and we're going to start naming it from this carbon or numbering it from this carbon because it's closer. It makes bromine be at substituent 2, and would make this be at substituent 3. So this substituent would be called 3-methyl. This substituent would be called 2-bromo. And for our root name, we have 5. So that's going to give us pent. And it's single bond. Oh, wait, we have a double substituent. We have another substituent here, another methyl at 2. Okay. So because we have another methyl at 3, we are going to write this as 3,3-dimethyl. Dimethyl. Right? The di is to tell us there's 2 of them at the same position. If they were not at the same position, we would still write it in the similar way, but we will now have to take accountability of where the other one is. Let's say maybe the other one was found on carbon 4 and not on 3, then we would have 3. So I think there's 6 here. So if that's 5, that's 6, there's 6. So it's not a pent, it's a hex. My bad. So if one was found at 4 and one was found at 3, we'll say 3, 4, and we would still say dimethyl. Now, when we are writing the whole name, the di doesn't make a difference. We are only interested in the methyl part, where M now is going to be at the end of our alphabet. So we would start it with the bromo. We would say 2-bromo. 3-dimethyl. Hexane. It's single bonds everywhere, so the suffix is going to be an A. Okay, let's take a look at another one. Okay, so here is our chain. Clearly, the longest chain we can see is this one over here, and we're going to start numbering that as carbon 1, reason being because of that functional group and also the substituent is really close. So we have a substituent at carbon number 2, which is a 2-methyl. There is 1, 2, 3, 4 carbons, so that's bute. And we can see that the double bond is at carbon number 1. So that's going to bute 1-ene. Then when we put it together, it's going to be 2-methyl bute 1-ene. Let's then go to alcohol. So here is an alcohol. Again, this is our functional group. Therefore, that's carbon number 1. We can see that this is clearly our straight line. There's 1, 2, 3, 4 carbons. So that's going to be a bute. We then need to take into consideration where that alcohol is, and that alcohol is at carbon number 1. So we're going to write that as butan 1-ol. Butan, please note you have to add that extra an. Normally it's just but. You have to add that extra butan 1-ol. Okay. Butanol. Then we're going to move to our carboxylic acids. You will never find them giving you a carboxylic acid with a substituent. So don't necessarily have to worry about that. If you have seen questions where they have given you carboxylic acids that have other substituents, you can send them to me and I can help you name those. So for carboxylic acid, mostly it's always going to be a straight shape. This carboxylic acid has 2 carbons, and that's going to be S. So to finish the name, we just write an oic acid at the end. So this is ethanoic acid. Okay. Let's have a look at aldehydes and ketones. Yeah, we have an aldehyde that has 3 chains. Again, with aldehyde and ketones, chances of them giving you something more complex is not there. So we have an aldehyde that has 3 carbons, and the thing about the aldehyde is that the carbon will always be in the double bond with oxygen will always be in number 1. So you don't have to actually indicate where it is. It's always just going to be propanol. There's no indication because with aldehydes, your double bond with oxygen is always carbon number 1, always. Now, with ketones, it's not going to be number one. It should never be number one. If it's number one, then it's an aldehyde. So then you would have to indicate the position of your double bond with oxygen. Here we have pentan. Please note the "an" that they add. So you can see with the alcohol and with the aldehyde and the ketones, you have to add that "an." Propanol, pentanon. Please add that extra. The other ones you saw, you don't need to. You can just say butanoic acid, butane. There's no adding of this extra "an." Right. So you have to show the position and write the suffix there. Nothing too crazy there. And then we have the esters. So the esters are actually a combination of your alcohol and carboxylic acid. So the naming of your ester is dependent on which part comes from the alcohol and which part comes from the carboxylic acid. The one that comes from the carboxylic acid, we would add an anoate to it, and the one that comes from the alcohol will now act as a substituent, so we will add a lye to it. So how do we tell which part comes from the alcohol or which part comes from the carboxylic acid? If you can remember, the carboxylic acid does have a double bond with oxygen, whereas alcohol does not have a double bond with oxygen. So this part over here comes from the carboxylic acid. So we would count the number of carbons we have. According to this, we have 4. So because it's coming from the acid, it gets an anoate at the end. So this is going to be butanoate. Whereas the part that comes from the alcohol, you can see it has a double single bond with oxygen there. It gets a lye. So because there's 2 of those carbons, we just write the eth and the lye. So together, it's just going to be ethyl butanoate. Ethyl butanoate. So it's very important for you to see where the double bond is and say, okay, that's where the carboxylic acid comes from. That's where the alcohol comes from. And this is how I'm going to name them. Okay, but we'll definitely look at esterification in more details. So the next thing we're going to look at is the properties of our organic molecules. The properties of our organic molecules is dependent on the functional groups. And the functional groups will tell us what type of intermolecular forces we have. We know with regards to intermolecular forces, we have the van der Waals forces, which have the hydrogen bonding. We have induced forces. We have the London dispersion forces, right? The dipole forces, London dispersion forces, and the hydrogen bonds. Those are the 3. So depending on your molecule, we will then say whether or not it would have a high boiling point or a high vapor pressure. So let us look at how the intermolecular forces influences. If you have a weak intermolecular forces, then we have example here. We have induced dipole, which is your London dispersion forces, dipole forces, right? Then we would require little energy in order for us to break the bonds that exist. So therefore, you would have a lower boiling point. And if you have weak intermolecular forces, because you require little energy in order for the molecules to break away from the liquid and form vapor, then a lot of it will form vapor. And that's why you're going to have a high vapor pressure. So you can see that these two are inversely proportional. When one is low, the other one is high, which makes sense. If you require little energy, then a lot of it is going to evaporate, forming that vapor pressure. If you have a strong intermolecular bond, which will mostly just be hydrogen bond, then you're going to require lots of energy in order for you to break the intermolecular bonds that exist between molecules for them to move away from each other. Therefore, you would require a higher boiling point, and because you're not boiling off that much of the liquid, then you would have a low vapor pressure. So the two are inversely proportional. So to be more precise, let's look at which homologous series have weak and strong intermolecular forces. So the ones that have the weak intermolecular forces include your alkane, your alkenes, your alkynes, and then you have your halogenes, your esters, your ketones, and your aldehydes. These over here would have the dipole-dipole forces. These over here would have the London dispersion forces, or what we know as the induced dipole forces. Therefore, they would have weak intermolecular forces, less energy needed to break the bonds, lower boiling point, higher vapor pressure. Now, the way they have drawn them here, or written them out here, shows you which one has the highest intermolecular forces. So alkanes, in this case, although alkanes, alkynes, and alkenes and alkynes have induced, the strongest would be the alkanes. If you were to compare a triple bonded alkyne to a single bonded, this would require more energy to break than that. Then in terms of haloalkanes, esters, ketones, aldehydes, you can clearly see this is weak for the dipole-dipole forces, and this one has a much stronger dipole-dipole force. Then we have your hydrogen bonds, which will only exist for your alcohols and your carboxylic acids, but the carboxylic acid is much stronger than the alcohol because it has two sites. That is very important to note down because they will ask you why is both of them have hydrogen bonds. Why is the carboxylic acid much stronger than the alcohol? It's because the carboxylic acid has two sides. The thing about chemical bonds is that they're not necessarily certain. So that double bond and oxygen can actually exchange with one another. So there will be two sides for hydrogen to have, two sides for the hydrogen bond to happen instead of one, whereas alcohol only has one oxygen, so there's only one side for the intermolecular forces to exist. So these are considered strong intermolecular forces, therefore we would require more energy to break them, and that is why they have a much higher melting and boiling point and a lower vapor pressure. Now, the next thing that can influence your property is the shape, or actually the length. Let's put it this way, the shape and the length. But first, let's look at the length. The length of your chain. Let us compare this molecule to that molecule. This one here has a longer length, so there would be more sites for intermolecular forces to be found. Where this one is a bit shorter, so there we have fewer sites where intermolecular forces are found. Now, for the ones that have a short chain, because there's fewer sites for the intermolecular forces to take place, we would then have weak intermolecular forces between them. And this would mean that we would require less energy, therefore there would be lower boiling point and higher vapor pressure. Whereas if we have a longer chain, we can clearly see we have more sites for the intermolecular forces to take place. So we would have a much stronger intermolecular forces, and that means we would require more energy, and that's why we have a higher melting and boiling point, leading us to a low vapor pressure. Now we're going to take a look at how the chain of our intermolecular forces, of our molecules, affect the boiling point, or in this case, the properties. So these two have the same amount of carbons, but the problem is that this one here has substituents. This one here is just long. So this, because of its substituents, it would have less sites for the intermolecular forces. And because this one is just long, it would have more surface area for the intermolecular forces. So when we have a chain that has branches, it would have weak intermolecular forces, therefore less energy is required to break the molecules from each other. That means a lower boiling point and a higher vapor pressure. If the molecule has a straight line or a long straight space, then we know they will exert stronger intermolecular forces, and more energy is going to be required to break those bonds. Therefore, we would have a higher melting point and a lower vapor pressure. And that is how those would then influence the intermolecular properties.